So in yesterday's class, we have discussed the concept of numerical aperture and acceptance angle, and how a light ray can be propagated by an optical fiber, and the different types of optical. Yes, 103. What is this? So different types of optical fibers are also we have discussed. So numerical aperture, it represents the light gathering capacity of an optical fiber, which is a dimensionless quantity. So a light ray should enter at the left end of the optical fiber because it is a information carrying wave. And when it enters the left side of the optical fiber, then diffraction takes place. Again, it incident on the core cladding interface. Here it is traveling from denser medium to rarer medium. When the condition for total internal reflection is satisfied, that is, the angle of incidence at the core cladding interface is more than critical angle, it suffers total internal reflection. Again, it travels in the core medium at the bottom surface. Again, the angle of incidence is more than critical angle. In this way, it suffers multiple reflections and it can be propagated from one end of the optical fiber to the other end. So this is the propagation of light to an optical fiber, and numerical aperture sin alpha or sin im is under root n1 square minus n2 square. And also we have defined a core cladding interface, core cladding index difference delta is n1 difference n2 by n1. And we have obtained the expression for numerical aperture. Numerical aperture is sin alpha, which is under root n1 square minus n2 square. And basing on the material and the mode of propagation and refractive index profiles, the optical fibers are classified. Basing on the refractive index profile, they are classified as a step index optical fiber and gradient index optical fiber. So in step index optical fiber, core has a uniform refractive index N1 and cladding is also having uniform refractive index N2 and N1 is greater than N2. So only at the core cladding interface, the angle of incidence is more than critical angle, it suffers total internal reflection. So stepwise only at that point only, it has to travel till the core cladding interface, then only it suffers total internal reflection. This type of fiber, this is called as a step index optical fiber. And the gradient index optical fiber is, here the core has a non-uniform refractive index that decreases gradually from the center of the optical fiber to towards the core cladding interface. So from center of the fiber, at each and every layer, the light is traveling from denser medium to rarer medium, and there is finite probability that the angle of incidence is more than critical angle. There itself, it suffers total internal reflection. So it takes a helical path, and the possibility of overlapping of two light waves is minimized here. So these material, these optical fibers, these are called as gradient index optical fiber. And basing on the modes of propagation, again optical fibers are classified into a single mode optical fiber and a multi-mode optical fiber. Only one signal or one optical pulse is allowed to incident or pass at a time. Then it is called as a single mode optical fiber. So here for communication, this is very required without any distortion, but information capacity will be decreasing because only one signal we are sending at a time. So you have a step index single mode optical fiber, then step index single mode multi-mode fiber, and the gradient index multi-mode fiber also you have. And in multi-mode fiber, two or more signals or more than two signals can be sent at a time. So more information can be sent, but there is a possibility of overlapping and distortion in this case. So it can be addressed. Once it is addressed properly, more data or more information can be sent from one end of the optical fiber to the other end of the optical fiber. And the third category based on the material profile. Some maybe you both core and cladding are made up of glassy materials. Sometimes they made up of plastic, or otherwise it is a combination of both the glass and the plastic. So like that, optical fibers can be fabricated. So this is the classification of optical fiber based on the modes of propagation, based on the materials, and based on the refractive index profiles. This we have discussed in the last class. Now next one is double crucible method. You have to how to fabricate an optical fiber. One important method is there, which is called as double crucible method. Is this visible? PPT? Students?
Yes, sir.
Oh. To please take this diagram, double crucible method. You must draw this diagram. So the technique by which you can prepare an optical fiber, such an important technique is the double crucible method. Please you take this diagram. First I'll explain, then we'll share the notes for this. Two crucibles are there, and the core glass type is in the inner crucible. The cladding is placed at the outer crucible, and it is connected with the furnace. More nozzles are there. Explain how this method will work. Please take the figure. Shall I start explanation, students? Boys?
Yes, sir.
Okay, double crucible method. It is a technique by which you can produce an optical fiber of desired length. And the double crucible method was developed by actually British Post Office with collaboration with Nippon Glass Company. Nippon Company, Japan is famous for all this glassy material fabrication of glass materials. And for the British Post Office means it's a British communication system. Both collaborated and they have designed this double crucible method to fabricate an optical fiber. In this method, optical fibers with attenuation values below 5 decibel/meter. So it's very the power loss is optical power loss is very less. They can be fabricated. And coming to the construction of double crucible method, in this method, two very high purity glass rods with different refractive indices are prepared using conventional techniques. Because one should be for core material and second one should be for cladding material. Same material, if you change the impurity, if you add some impurities or change the concentration, the refractive index profile will be changing. So the impurities are added to both glass rods in such a way that one act as a core material and another one act as a cladding material, because the refractive index of core should be greater than that of cladding. So basically these are made with sodium borosilicate materials with different compositions for core and cladding. So because of different compositions, the refractive index profile will be changing. Core has more refractive index when you compare it with the of cladding. So M1 is greater than, then only light passes from denser to layer and medium, total internal reflection takes place. So to draw optical fibers from these glass rods, two cylindrical crucibles are arranged concentrically as shown in the figure. So in the previous figure, we can see, so in this, so two crucibles are there. The first one is, this is inner crucible. In this, the material glass rod, which can be used as a core material, can be inserted like this. It is surrounded by another coaxial cylinder, and that's why it is called as a double crucible. Another crucible. In this, another glass rod, which acts as a cladding material, can be inserted, and both are connected to the furnace. And generally, the furnace temperature will be maintained between 850 degrees to 1100 degrees centigrade approximately. So a core rod and a cladding rod, initially they kept at the top of the crucibles as shown in the figure. Furnace is both sides furnace is there. Initially The crucibles are heated to very high temperature between 850 degrees to 1100 degrees centigrade. When the crucibles are attained the required temperature, then slowly the glass rods, both core material and also the cladding glass rod, both are inserted in the crucible. Because of the high temperature, these glass is melted and it fills the crucible with the molten glass form. So the melted glass will be occupying the crucible, and finally they reach up to this. So by using pressure, and they are forced to come through these nozzles initially. So initially the core glass type material will be coming in this, then this molten form of cladding is allowed to pass through this. So it is inside inner region will be core, and it is surrounded by cladding type material will be obtained there. So initially the glass rods are fed slowly downward in the heated crucibles. Due to high temperature, the glass rod will be melted and fill the crucibles with molten glass. Then at the bottom, the crucibles are tapered down to concentric nozzles. Small concentric nozzles are there where melted glass is pulled to a fiber, so that the cladding surrounds the core, and the pulling speed is given by the rotating drum onto which the fiber is wound. Like that, it can be wound on the given pulling drum. Finally, a plastic coating is done on the cladding layer. As we discussed, a protection layer is required. So a three-layer optical fiber cable can be fabricated, and by this method a fiber can be continuously fabricated from the molten glass. So in the second figure you can see, so this is actually the experimental technique. Two glass rods are there, and the two crucibles, two vessels are there, and they are connected to a furnace, and diameter also can be monitored, because core diameter and cladding diameter, they are very important, because which mode of optical fiber you want to fabricate. If it's single mode, it is around 5 micrometer, very less diameter should be there for the core material. For multi mode, you need more diameter. So basing on the requirement, the diameter can be monitored by using an arrangement here. And at the bottom, as you see, a rotating drum will be there. Initially, the crucibles are heated to 850 to 1100 degrees centigrade in general. Then glass rods are slowly inserted in the crucibles, so that because of the high temperature, the glass material will be melted and molten form of glass is filled in the crucibles. Then they are allowed to pass through the concentric nozzles as shown in figure. Initially, core material allowed to pass, then surrounded by cladding simultaneously it will be done. The diameter can be controlled by using this arrangement. So finally, in optical another coating was done, plastic coating, so that it gives the strength and protection for the optical fiber. Finally, the optical fiber will be wound on the given rotating drum. In this way, an optical fiber of desired length can be fabricated, for which the attenuation loss is less than 5 days per meter. So this is the construction and working of double crucible method. Is this okay? Shall I explain once? Students? So in brief, if you take, so inner platinum crucible contains core glass rod, outer crucible contains cladding glass rod. So maintain the required temperature with the help of electric furnace. Electric furnace is placed on either side of the crucible, so the required temperature is maintained. And because of the high temperature, it converts the glass rods into liquid when they are inserted in the crucibles. Therefore, optical fiber is drawn at core as inner layer and cladding as outer layer. And finally, a plastic coating is also given, so that a three-layer cable can be drawn. At the bottom, you can observe concentric nozzles are there. The pulling speed is given by the rotating drum. So finally, after three-layer coating, inner layer should be coated. It is surrounded by cladding. Again, a plastic coating is done, and finally, it is wounded on the given optical fiber. So it was developed by British Post Office in collaboration with Nippon Glass Company Limited, Japan. By this method, optical fibers of desired length can be fabricated, for which the attenuation is less than 5 decibel meter. So this is the construction and working of double crucible method. Is it okay, students?
Yes, sir.
Now, losses in optical fiber. You take the heading. Last topic here. losses in optical fiber. Single mode, multi-mode also have some feature.
Sir,
So attenuation in optical fiber cable. So even though we assume, if you compare with the radio waves and microwaves, there is the power loss is negligible. But even though because of different reasons, some power loss will exist in optical fiber communication system. So in optical communication system, how much output power we are getting, it is less when you compare it with the input power. So this is called as optical power loss. So the power loss in an optical fiber is studied in terms of attenuation. So it is the distortion, and it is in terms of attenuation only we can measure the power loss in optical fiber communication system. So there are many reasons for power loss. So first one is improper cable coupling. That means the fabrication of a core and cladding. Suppose it is mismatched, and some power loss will be there because total internal reflection should occur properly. If that is not possible, then scattering will be there. Some optical power input can be scattered. Then second, the nature of the cable. That means the nature of the material. Because even though we assume the profile is refractive index profile is perfect, some deviation may be there, and absorption of the nature of the material, it may absorb. So 100% of light is not refracted, and because of that some power loss will exist. And the length of the cable, as the length increases, because of these reasons power loss will be more, which increases exponentially. So the length of the cable also reasonable reason for attenuation of the fibers, and the scattering of them. So the light gets scattered because of the inherent property of light wave. So these are the main reasons, so that the power loss or attenuation occurs in optical fiber communication system. So attenuation is the output power is not same as that of input power, which is less than the input power. This is called as power loss, and it is expressed in terms of attenuation. It may be because of the improper cable coupling or the nature of the cable, the absorption of light by the optical fiber, and because of the length of the cable, we have to transmit the data from kilometers sometimes. During that process, there exists some loss, and the scattering of light is also reason for the attenuation in optical fiber communication system. So, so attenuation is defined as it is a reduction in the signal strength. So with what strength the input optical signal is entered, the optical fiber is not same as that of transmitted through the optical fiber. So it is defined as the reduction in the signal strength or power when it is transmitted through an optical fiber. So it is generally measured in terms of decibel meter. So the optical attenuation is described in terms of decibel, which is represented by dB, which is a logarithmic unit. The decibel loss of optical power in a fiber is given as the loss in optical fiber is -10 log P output, power output by power input decibel. So this is the expression for the power loss in optical fiber communication system, where P out is the power emerging out of the fiber, P in is power launched into the fiber. How much power is entering in the left side of the cable and how much it is coming. So it is represented by P out. So the loss per kilometer is a standard unit, or sometimes it is per meter also a standard unit. Even for describing attenuation loss in all optical fiber designs, loss per kilometer is -10 by L log P out by P in decibel per kilometer, where it is the length of the fiber tested. And for lab-based experiments, we calculate the loss per meter only. So it is -10 by L log power output by power input decibel meter we will do when we are conducting the lab experiments. But in general, in an optical fiber communication system, the decibel per kilometer represents the attenuation in optical fiber communication system. This is the attenuation that occurs in optical fiber communication system. As we discussed, by transmitting the signals through the optical fiber, some energy will be lost due to few reasons. One is transmission losses, and another one is distortion losses. Because of the transmission, and also the nature of the light also some loss will be there. Again, transmission losses. This is absorption loss, scattering losses. These are the main reasons. So core material or of a fiber absorb few of the light, so that the input some of the amount is absorbed. The core itself, which cannot be refracted. Because of that, some losses will be there, and the light scatters. Because of the scatter is another parameter for optical attenuation. These losses in a fiber arises due to microscopic variation in material density. We assume that material is uniform, but the density will be changing. The refractive index also will be changing. You can't say it is homogeneous. Because of these reasons, light gets scattered, and this type of loss it can be called as scattering losses. And the third one is a distortion or bending losses. So the distortion of the fiber from the ideal straight line configuration may also result in losses in fibers, because the light bends cause some of the light not be internally reflected, but to propagate into the cladding and be lost. So because of the bending of the cable, actually the light should move straight so that it can reach the other end of the optical fiber, but because of the bending, it may scatter through the cladding material. So these are called as bending losses. There are many reasons for this losses in optical fiber. Broadly, they are classified into these types: improper cable coupling, the nature of the cable, the absorption of light by the core material because of the cable bending, which are the scattering losses, and as the length of the fiber increases, the scattering loss also will, the loss also will be more, and because of the scattering of light. And the general expression for power loss is 10 by L into log of P in by P out, where L is the length of the fiber, P in is power input, P out is power output. So you should remember this expression. And so attenuation, the optical power loss is expressed in terms of attenuation. So attenuation, it is defined as a reduction in the signal strength of power when it is transmitted through the optical fiber. It is measured in terms of decibel, which is a logarithmic unit, and the loss in optical power is represented by minus 10 log P out by P in decibel. Generally, it is expressed in terms of kilometers. So loss per kilometer is minus 10 by L log P out by P in decibel per kilometer. But for basic experiments, it can be treated as meters only, decibel meter only we can say. And the losses by transmitting the signals through the optical fiber, some amount of optical energy will be lost. It is because of transmission losses and distortion losses. And again, transmission losses, they occur because of the absorption of light by the core material, and the scattering because of the bending of the light also. You will be observing this, and also because of the refractive index profile and the density of the material. They may not be having uniform density, or refractive index will be changing. Because of that, some scattering losses will be there, and due to bending also, the light has to travel straight. Because of the bending, reflection or total internal reflection may not occur properly, and some amount of energy, optical energy, is scattered through the cladding material. These are the various reasons for power loss in optical fiber communication system. So you should write only short notes on optical power loss. You should define what is the optical power loss. Yes, 103. And how it is expressed. The unit for attenuation is expressed in terms of attenuation. What are the different reasons for power loss? And again, they are because of transmission losses, and how transmission losses will occur in optical fiber cable, and the distortion or bending losses also. You should describe with these diagrams. I think it will be sufficient. And finally, you have the applications of optical fibers. So there are many applications. All I think. So in television transmission, all these Hathway, Geo, whatever, so it is based on the optical fiber communication. So television transmission for entertainment, we use optical fiber. Even the data also, digital cameras, optical fibers are using. And imaging techniques for 3D animations and the three-dimensional like imaging of objects is optical fiber communication, because of the many advantages, low cost, there is no electromagnetic interference, and simple principle it works. And sea communication also, I think last year only one optical fiber cable was put under sea between Andaman Nicobar and Chennai. How I think around 2000 kilometers it seems. to that optical fiber. It connects India digitally. Andaman and Nicobar belongs to India only. So I think last year only it was installed and inaugurated by our Prime Minister. And in medical purposes, endoscopy, they use this optical fiber technology. Thin optical fiber cable in that some light beam is allowed to pass through the body so that it can take the images and they can be magnified in the where actually the problems are there, tissues are there, some bacteria is there, or some distortion is there in the muscles, everything which is called as endoscopy. So it is based on this optical fiber communication only, and the space shuttles and the data networks. So all our data is based on this optical fiber because it's the transferring speed is very high. So no 5G or whatever. So all they are based on this how with what capacity the data can be transferred. This is very important in this digital world. Probably these optical fibers are playing an important role. All we have observed during global pandemic, all are we are connected digitally only. There is no physical distance. So these are the few applications of optical fibers. So in this chapter, we have discussed what actually the importance of optical fiber communication system, what is the structure of an optical fiber, and the principle behind optical fiber, optical construction of an optical fiber, how it transfers the data in terms of in the form of optical pulses from one end of the fiber to the other end of the fiber, how the light can be propagated to an optical fiber, and the parameters involved in optical fiber communication, numerical aperture and acceptance angle we have discussed. Then expression for numerical aperture also we have discussed. Then the types of fibers based on the diffractive index profile, modes of propagation, and the nature of the material. The classification of optical fibers are also we have discussed. Then we have discussed the double crucible method, which can be used to fabricate an optical fiber cable of desired length with much less attenuation. Then we have discussed the losses in optical fiber or attenuation in optical fiber communication system. And finally, we have discussed few applications of optical fibers. This we have discussed in this chapter. So in this sense, this chapter is completed. So entire unit 4 is completed. And today, within 20 or 25 minutes, I'll give introduction and I will start the quantum introductory part of wave mechanics or quantum mechanics. So any doubt in this optical fiber communication system, students, let me know. Students, please respond. Is it okay this chapter? Girls?
Yes, sir.
Boys? No response from boys side?
Sir.
Only 48 are there in the class. Once I am finishing, many will join. Okay, so next chapter is unit 3. In this, the first chapter is wave mechanics. You take the heading wave mechanics. Today only I will discuss the introductory part and de Broglie wavelength. Up to that, I'll try to cover. Then we will see where. So we have this de Broglie concept of matter waves in the intermediate itself. Can you tell what actually dual nature of matter or dual nature of light? Matter waves. Do you have any idea, students? Is it there in your intermediate? Respond. Tarun, 99. 99 is there in the class?
Yes, sir. Yes, sir. I'm there.
What is the concept? What are matter waves? You have any idea? Anybody?
Sir, any particle which is in motion have some wave nature, sir.
Wave nature. Good. At least you have answered. What is dual nature of light?
So light moves in wave and particle form.
Yeah, very good. Can you give an example for that, Harshit?
like interface diffraction.
Yeah, yeah. Okay, fine. So little bit this you should understand the concept of this wave mechanics. There only you can easily know the Schrodinger equations and applications of these wave mechanics. So the branch of physics that deals with the relation between matter and radiation, or wave and mechanics, mechanical behavior. This branch of physics, this is called as wave mechanics or quantum mechanics. And the origin of this wave mechanics is de Broglie's concept of matter waves. And after Newton's first law, second law, and third law, all these kinetics and kinematics have been developed. And the mass, length, and time are taken as fundamental units, and any other unit can be derived by using these fundamental units. Like that, all these have been developed. Kinetics, kinematics, and the industrial revolution is also because of that. Then there are many theories are evolved, like the photoelectric effect given by Einstein, and also the quantum effect. Also, we have Heisenberg uncertainty principle, then de Broglie's concept of matter waves. So they actually they brought revolution among the science, because initially when matter is divided into small particles, they have stopped somewhere else. But man tried to find the minimum size of the particle in nature. So in that sense, some molecules have determined, their structure of atom is determined by and Rutherford experiment, all you are known. Then atom is consisting of number of electrons. You can call it as a sea of electrons, electron cloud, and the nucleus, small nucleus, is consisting of millions of protons and neutrons, like that. Then once they find that these Newton's laws are not applicable for these particles, because if you take third law of Newton, to every action there is an equal and opposite reaction. You cannot apply for the particle like electron. If the ball hits the wall with the same energy, it comes back. It is Newton's third law, but it can't be applicable for particles like electrons, protons, neutrons, etc. So again, some new models have been introduced to explain all this. And in that, an important theory is Planck's radiation law and Einstein theory of relativity. And from that, another important concept has been introduced, which is quantum mechanics or wave mechanics. The origin for this is, as Harshit rightly said, dual nature of light. So entire universe, if you take in the creation, it is either in the form of matter, material particle, or radiation or waves. So entire universe, either it should be in the physical form or in the energy form, which is radiation. And these are interconvertible. E is equal to mc square Einstein relation. So the dual nature of light is initially introduced because certain phenomena like interference, diffraction, polarization, all these are explained on the basis of the wave nature of light. The phenomena of interference, when two light waves are having same phase or constant phase difference, then allowed to propagate, superimpose over each other. At some places the intensity is maximum, at some places the intensity is minimum. So the redistribution of intensity due to the superposition of two light waves is called as interference. Similarly, the bending of the light around the edges of an obstacle is called as diffraction. So all these phenomena, interference, diffraction, polarization, all these are explained on the basis of wave nature of light. And if you take the phenomenon of reflection or the photoelectric effect, quantum effect, all these are explained on the basis of corpuscle nature or particle nature of light. So sometimes light behaves as a wave, and sometimes the light behaves as a particle. This is called as dual nature. So de Broglie proposed that light wave, a material particle can also be associated with the wave. So this wave is called as matter wave, because what his logic was, entire universe is either filled with light or or matter, and light possesses dual nature. So a material particle can also be associated with a wave, which is called as matter wave. So this is the fundamental aspect of deep Brooklyn. Further, he took two examples. So the first one, there is a principle in mechanics which is called as principle of least action. According to principle of least action, a particle it chooses a path such that the action should be minimum. So according to principle of least action, always a particle will chooses a path so that the action should be minimum. So a particle has to move from one point to another point. What is the short distance? Which one is the short distance? You want to move a particle from point A to point B. So which is the shortest distance?
Straight path.
It is a straight line, straight path. You can draw infinite number of curves from A to B, but what is the minimum path? It is the short straight line. Even human tendency is also like that. If you are driving, you are moving with a bike. So always you find the shortest path so that you can reach the destination. So that the action should be minimum. Within minimum time, you can reach the destination. So this is a human tendency. This is also the nature of a particle. So according to principle of least action mechanics, always a particle takes a path so that the action should be minimum. And surprisingly, this is similar to the Fermat's principle, which explains the property of optical pulses. According to Fermat's principle, light always takes a path in medium or in space so that the time of transit is minimum. The same is applicable even for light energy. So light also during its propagation, it takes a path so that the time of transit is minimum. If the minimum time it should reach the destination is the nature of light. This is similar to a material particle. A material particle also always takes a path so that the action should be minimum. So this is the first similarity. De Broglie De Broglie takes this example as a reference. And the second one, the stable states of electrons, they follow integer rules because they follow orbital angular momentum, spin quantum numbers. By these rules only, different electrons will be occupying different energy levels. And these integer rules are also applicable for vibration of strings executing simple harmonic motion. You take a spring, you add some load, you pull in the downside direction, so it oscillates, which are simple harmonic in nature, and the energy is quantized. That means the energy of a simple harmonic oscillator, it follows quantum rules, and these quantum rules are also applicable for electrons which are moving in stable states. Electron is referred to be a radiation, it's a wave only. That means there is a similarity between a wave and a material particle according to these quantum rules. And also from the principle of least action, always a particle takes a path so that the action should be minimum. And according to Fermat's principle, light always takes a path so that the time of transit should be minimum. So by taking these two similarities, de Broglie proposed that light has a dual nature. Entire universe is mixed either with light or material particle. So material particle can also be associated with a wave, and this is called as a matter wave. And by taking the analogy, by taking Planck's radiation law, he gave an expression for the matter wave and wavelength of the matter wave associated with the particle, which is given by lambda is equal to h by mv. This we are going to discuss later. And in these two or three important theories have been established. One is Einstein's theory of Einstein's special theory of relativity. So according to the fundamental concept of Newtonian mechanics, mass, length, and time are taken as absolute quantities. So any other physical quantity can be derived from these quantities only. But strictly these are applicable for particles or systems which are having velocity much less than velocity of light. Systems or objects having comparable with velocity of light. These Newtonian mechanics are not valid. So this is the I think you know this popular story also. Once Akbar, in the floor of his court, drew a line in the floor of the house and asked the wise man, make it small without rubbing. Okay, so what should be the answer given by Birbal?
We will draw a small line below it, sir.
Bigger line, bigger line. Make it small without rubbing. So you should draw a bigger one. Yes, you are right. So Akbar drew a line on the floor of his court and asked the wise man, make it small without rubbing. Then what you should do? If you draw a bigger one, it automatically becomes small. So that means the length is not an absolute quantity, it is a relative quantity. If you compare mass of electron with the mass of cricket ball, mass of cricket ball is more. If you compare mass of cricket ball with mass of mass of football is more. Even though there is no change in the mass of the cricket ball, if you are comparing with electron, it is more. If you are comparing with football, it is less. So mass is also not an absolute quantity, it is a relative quantity. And intermediate also have studied the Doppler effect. The apparent change in the frequency due to the relative motion between source and observer is called as Doppler effect. So when the train is approaching you, you feel that the frequency is high. When the train is moving away, you feel that the frequency is low. And when you are relatively constant with respect to each other, then you assume that the frequency is same. So even though there is no change in the frequency, due to the relative motion between source and observer, the frequency seems to be changes. So frequency is also not an absolute quantity; it's a relative quantity. That means energy is not an absolute quantity. And also time. Time is, of course, it is a relative quantity because the time now in India is different than the time in America. It is because of the rotation of the Earth. So for us, it is a daytime. For US, it is a night time. So time is also not an absolute quantity. It is a relative quantity only. It is because of the motion of planets around the sun. If Earth completes one revolution, it is 1 year for us. If you take another planet, if you say stay in another planet, if it takes more time, then 1 year is more for them. That's why we call angels or devatas, they have long lifetime because of this motion only. They take more time to fly. So this is the beauty. Time is also an absolute quantity, it's a relative quantity only. So Einstein proposed that mass and energy are interconvertible. The equation is delta E is equal to delta M into C square, where delta E is change in the energy, delta M is change in the mass. That means energy may be changed with mass, change as mass, or mass can be changed to energy if they travel at the speed of c. That's why c is there, which is speed of light. So particles are systems. If you acquire the speed of velocity, then mass and energy are interconvertible. I think 20 years back, one movie was there, Aditya 360 and something, some hero is there, and the scientist he designed a space tracker. So if you travel along the positive x-axis, you can time axis, you can see your forefathers. If you go in the negative time axis, you can see your if you go negative x-axis, you can see your forefathers. If it moves in the positive time x-axis, you can see your next generations also. So time is a relative quantity only, and length is also a relative. Mass is also a relative. Those who have prepared for IIT, you can have this expression m is equal to m naught by root of 1 minus v square by c square, where m is the mass of the particle in motion, m naught is the rest mass. That's why even in semiconductors, we have taken the effective mass of electron or effective mass of hole by calculating the concentration. So all these fundamental quantities, which in kinematics we assumed absolute quantities, coming to electrons, photons, and neutrons, they are not absolute quantities; they are relative quantities only. So this is the theory of relativity. And one more important theory was introduced, which is the Heisenberg uncertainty. So according to Heisenberg uncertainty principle, it is difficult to find simultaneously both the position and momentum of a particle like electron to any desired degree of accuracy. So for a ordinary particle moving with a limited speed, if m1 is the mass of the particle, u1 is its initial velocity, then momentum is m1 u1. Similarly, after some time, the velocity will be changing, it becomes u2, the momentum will be m1 u2, and you can calculate change in momentum, and also the position momentum can be measured simultaneously. But if you want to find out the position and momentum of a particle like an electron, then you can't measure simultaneously. I'll give you a simple example. Any object can be seen by the reflection of light. Suppose I want to see the face of what we can say, row number 87, Vijay Kirti, then what should be the principle? The light should incident on the face, it should get reflected. The condition is the size of the object should be comparable with size of the wavelength of light. If this condition is satisfied, we can see the images. Suppose I want to, this is a normal principle. Suppose I want to see a particle like electron. So what should be the condition? The wavelength of incident light should be comparable with the size of the electron. So size of electron is very minute. The size is very less. So the wavelength of incident light should also be comparable with size of electron. If wavelength is that much small, then frequency will be very high. Because wavelength and frequency are inversely related. If frequency is very high, then energy is also very high. So with that high energy, when the energy ray incident on the electron, what happens? The electron gets scattered. So if you want to find out the position of the electron, the momentum is becoming indeterminate. If you want to find out the momentum, the position will be indeterminate. So you cannot measure simultaneously the position and the momentum of the particle to any desired degree of accuracy. So this is called as Heisenberg's uncertainty principle. So there are three fundamental value of physical quantities which cannot be measured simultaneously for particles like electrons, etc. One is position and momentum, second one is angular displacement and angular momentum, and third one is energy and time. So these are the three pairs of physical quantities which cannot be measured simultaneously to any desired degree of accuracy. So this is so ordinary Newtonian mechanics, classical mechanics are not applicable for these materials. And one more theory is introduced, which is the Planck's radiation law, which is given by E is equal to hν. So black body radiation is not explained by classical theory. So according to quantum theory, we have discussed in the previous case, energy distribution is not continuous. Only certain distinct energy levels are possible, which is Planck's radiation law. So by taking all this, some model was developed by Schrodinger, which is called as wave mechanics or quantum mechanics. So what actually this wave mechanics represents, these are the mathematical equations. In the same equation, you can represent the dual nature of matter also. So in the left side, it is the particle which associated with a wave is represented in the left hand side, and the mechanical properties are represented on the right side like that. Within the same mathematical equation, the dual nature of matter is expressed. That's why these are called as wave mechanics. The wave is nothing but radiation, mechanics related to the material particle. So the combination of both, because it is the dual nature of matter proposed by de Broglie, there are the mathematical equations given by Schrodinger. These equations are called as Schrodinger equations. So this is the introductory part of wave mechanics. So in this we are going to discuss de Broglie concept of matter waves initially. Then he has introduced wave function associated with the matter material particle represented by xi or psi. Notation is psi only. And what is the significance of that wave function we are going to discuss. Then Schrodinger tried to develop certain mathematical equations. In these mathematical equations, simultaneously you can represent the wave nature as well as the corpuscular nature of the particle. Those equations are called as Schrodinger wave equations. We have to derive Schrodinger time dependent wave equation and Schrodinger time independent wave equation. Two derivations are there. And the application of Schrodinger time independent wave equation, which is a particle in one dimension box, that we are going to discuss in this chapter. So three derivations are there. For the next class, first you have 11 o'clock, you have your free, or you have any other class? Students? You have a regular schedule today? Varun?
Yes, sir, we have EG.
EG
Engineering.
at 11:10? 11:10?
Yes, sir, 11:10 to 1:20.
Okay, so I stop here then. So in the next class, first I'll explain what is de Broglie's concept of matter wave and the properties of matter waves, and the significance of wave function and Schrodinger time dependent equation we will discuss in the next class. And in one more class I require so that I can complete this Schrodinger time independent wave equation and the particle in one dimension box application of Schrodinger time independent equation I will discuss. And we complete that chapter, and only one chapter is the electromagnetic theory. That after completion of this one, I will take the electromagnetic theory, and most likely, most positively by tomorrow, I will share the PPT of this unit 5 lasers as well as. So I have to do some fine tuning lasers and optical fibers. Tomorrow I will share, and this time a common assignment will be given within 3 or 4 days. We have to complete the assignment, and you should upload it through Google Classroom. And most likely your internal exams, second internal exams are scheduled from 30th of March. So 30, 31st and 1st you have internal examination, because the 3rd is the last date of inspection. After that, from 6th onwards we have external lab examination. So it goes till 17th, because many sections have to complete. So 6th to 17th you have external lab examination. After that you have external theory examination. The schedule yet to be released. We are not sure about this, but this is there in the almanac. 31st and 1st we have internal examination, and from 6th onwards we have external examination, and one common assignment you should complete. And in this second internal, along with the question paper, a 5 marks quiz in the form of Google form, it will be given to you. You have to answer, because in the almanac, in the curriculum, 5 marks are allotted for quiz of some type, 5 marks for assignment, 5 marks for quiz, and 20 marks for your internal examination. It is calculated for 30 marks. So entire these 3 or 4 weeks you should be very busy, because 2 days you have to come to lab and you should attend all these labs. And online also theory will go on, and teachers will take, they have to complete the syllabus. So what we have to do is you compile the notes, collect the notes, and because you don't get time in the month of April, because April is the month of exams, you have internals, second internals followed by external lab examination. And as per internal lab is concerned, internal evaluation will be conducted during the lab, regular lab session only. If you are coming regularly and completing the experiment, that can be considered. Finally, a small viva will be asked, and the internal assessment will be done, and marks will be given for internal lab examination. So this is the pattern we have to follow in this curriculum.
Sir, even second mid is online or offline, sir?
We are planning online only, it's not offline. It's difficult for conducting for 1,000 students at this juncture, because already external exams are started for second, third, and fourth years. Most likely they are online exams for this time. But lab exams will be offline. External lab exams.
Sir, what about semester exams, external exams?
Semester exams offline only. You should go to another college and you should write the exams.
When, sir?
Which date is not announced by OU, but last week of April tentatively or first week of May they start. Got it? So respond for the attendance.
Present, sir. 61. Present, sir. 61 present.
62.
Present, sir.